Hello once more. For week 2, we begin a new topic which is all about matrices. So beginning with the operation with matrices. What are the objectives for the lesson? So you should be able to determine whether two matrices are equal. You should be able to add and subtract matrices and multiply a matrix by a scalar. Multiply two matrices. Use matrices to solve a system of linear equations. And partition a matrix and write a linear combination of column vectors. Now, how do we know whether two matrices are equal? It says here that two matrices A and B with entries A sub ij and B sub ij respectively are equal when they have the same size m by n. And A sub ij is equal to B sub ij for I from 1 to m and for j from 1 to n. So let's say we have an example here. Let us consider the four matrices given. We have A, which is a 2 by 2 matrix, B, which is a 2 by 1 matrix, or we refer to this one as a column matrix, and C, which is a 1 by 2 matrix, also called the row matrix, and D, which is also a 2 by 2 matrix. Matrices A and B are not equal since they are not of the same size, also with B and C, which are also not equal. But we can equate A with B, or we say since A and B are of the same size, we can see that A would be equivalent to D if X is equal to 3, because according to the definition, that A sub ij should be equal to B sub ij for all I and for all j, right? So as we can see here, you have A11 to B1, same with B11, A12, the same as B12. And then we also have A22 equal to B22. And so for these two matrices to be equal, then A21 should be equal to B21 when X is equivalent to 3. A matrix that has only one column is a column matrix, or we call it a column vector. And for a matrix that has only one row, we call that one as a row matrix or row vector. So what are the operations for matrices? We have matrix addition, subtraction, and scalar multiplication. To add two matrices, which is of the same size, we only add their corresponding entries. So say here, if A and B are matrices of size m by n, for which A has entries A sub ij and B has entries B sub ij, then their sum is the m by n matrix A plus B. So we only need to add element per element. So say A sub ij plus B sub ij. So the sum of two matrices of different sizes is undefined. So that's why before we can add matrices, we must ensure that they have the same size. Example, if you have here A, which is a 2 by 2 matrix, given in A is a pair of 2 by 2 matrices, and therefore we can find the sum. So we only need to add element per element, say negative 1 plus 1, that would be 0, and then 2 plus 3, that would be 5, and then 0 plus negative 1, that would be 7, 1 is equal to 3. So we only do it element per element. Okay, so similar with B, we can add them because they have the same size, which is A2 by 3. Also in the matrices or in C, wherein we have two column vectors. So as you can see here, one, we have a column vector with entries 1, negative 3, and negative 2. Adding that one with column vector which has entries negative 1, 3, and 2, resulting to the zero matrix. Okay, so we can see here that one of the matrix is just the negative of the other. Right? So that when we add, then the result is just 0. And for D, we can see that the sum is not defined, primarily because the first matrix, which is a 2 by 3 matrix, is not the same with the second matrix, which is a 2 by 2 Now, how do we perform scalar multiplication? If A is a matrix that is m by n, that is the size is m by n, with entries a sub ij and c is a scalar, then the scalar multiple of A by C is the m by n matrix CA. So we only need to multiply every element of A by the scalar C so that we can come up with an element equivalent to CA sub ij. Example, for the matrices A and B, find 3A. So here we only need to multiply every element of A with 3 so that we will have here 1 times 3 is 3 times 2 that will be 6 times 3 that will be 12 times 3 of this is negative 9, 0, and then we will have negative 3. 3 times 2 is 6, and then we will have 3, 6, and we have 6, 3, and 6. What about for B? So we only need to find the negative of B. So just apply the opposite sign of the given entities. So we can have here negative 1 times B. So we simply apply the negative of everything. Come out B. And for 3A minus B, since both are of the same size, then we can perform the addition element-wise. Now, when you have matrix multiplication, you may think of it as like multiplying the numbers, but actually it's not. So if we can see here that with matrix multiplication, there is some condition to satisfy. So for example, if A is an n by n matrix consisting of elements A sub ij, and B is an n by p matrix, is an n by p matrix consisting of B sub ij elements, then the product AB is an n by p matrix. So it's like if you have here, an n by n. So say, okay, so say I have A. So say I have A here, which is an n by n matrix. Multiply it, okay, say by B, which is an n by p matrix. We can expect that the product AB is defined whenever the number of columns of the initial of the first matrix is the same as with the number of rows of the second matrix. So we have here same number, okay? So that the resulting matrix will have a size that is equivalent to m by p, okay? So again, for us to be able to determine whether the matrix product is defined, the number of columns of the first matrix should be equal to the number of rows of the next or of the second matrix. Hence, we will have the size of the product to be an n by p, okay, which consists of elements C sub ij. Okay, so that's how we perform matrix multiplication, and then Cij will be equivalent to the sum of your A sub ik and B sub kj from k equals 1 up to n. So that we will have your ai1 times b1 times j, plus you have ai2 b2j plus ai3 btj plus so on and so forth until we will have ai times b sub nj. Now let us try to do that one. So we have here A and B. So first thing that we need to do in order to find the product is to assure or to make sure that the number of columns of A is the same as the number of rows of B. So since we will have A to be a 3 by 2 matrix and B to be a 2 by 2 matrix, since the number of columns of A is the same as the number of rows of B, then we can come up with a product whose size will be a 3 Okay, so in order to find the elements of the product AB, so what we can perform the row and column multiplication. So for example, I have here the product AB, which is a 3 by 2. So say this one. And let's say let's name the entries as C11, C12, C21, C22, C31, and C32. So for us to be able to know what C11 is, what I need to do is to multiply row 1, this one, to multiply row 1 of matrix A, multiply row 1 of matrix A with column 1 of matrix B. Okay, so that what do we have? And add all the products. So we have -1 times -3, that will be +3, and then add that with -12. So we have 3 minus 12, so that will be -9. Okay, so similarly, I want to find what C12 is. So to find C12 is, I only need to multiply again first row of the first matrix with the second column of the second matrix. So you have -1 times 2, that will be -2. -2 plus 3, that will be +1. So similarly, okay, repeating the same process. So we want to find C21. So that means I'm going to multiply second row of the first matrix with the first column of the second matrix. We have 4 times -3, that would be -12, -12 plus 8, that would be -4, right? So -12 plus 8 is -4. And then again, to find C22, we're simply multiplying second Okay, we're multiplying second row by the second column of the next matrix. So that will be 4 times 2 is 8. 8 minus 2, that is 6. And of course, to find C31, we are multiplying the entries of row 3. So multiplying the entries of row 3 with the entries of column 1 in matrix B. So you have 5 times -3 is -15 plus 0 is -15. And then to find C32, we will have 5 times 2, that will be 10 plus 0, that will be. So this is how you find the entries for the matrix product. Okay, we can check our answer in the next slides. So again, you simply multiplying the first row of column A with the first column of B, that finds an NP, and we perform that one until we find the last element, which is C32, and we can check our answer, which is -9, 1, -4, 6, -15, 10, which is just the same as our answer. How about systems of linear equation? How do we apply this matrix operation into, how do we apply them in systems of linear equation? Now, one practical application of matrix multiplication is representing a system of linear equations. Previously, we were able to write the system of equation into an augmented matrix and work on the matrix with elementary row operations, right? To come up with finding the solution. Once we perform the elementary row operation until the augmented matrix has been transformed into a row echelon form or reduced row echelon form. Now, this is a different thing. What we are going to do now is to express a system of linear equation into a matrix equation. So we have here, we have for example, we will have a system of 3 linear equations with 3 unknowns, x of 1, x of 2, x of 3. And Okay, what we're going to do is we're going to write it as a matrix equation AX equals B. So where A is the coefficient matrix of the system and X and B are column matrices. So first of all, we are going to isolate all the coefficients and write it down as the coefficient matrix A. And then we're going to write down the unknown, or we call that one as the solution vector x sub 1, x sub 2, x sub 3, which is your x. And then the constant, all the constants are in this column vector B. Notice that if we're going to apply our multiplication of matrices, the product AX equals B will definitely be equal to this system of equation. So say you have A11 times x sub 1, that will be this one. A11 times x sub 1 plus A12 times x sub 2, that will be this, plus A sub 13 times x sub 3, it is equivalent to B. So recalling the element wise, right? So, and also for A21 multiplied by x sub 1 here, plus A22 times x sub 2, that will be this one, and A sub 23 times x sub 3 to be this, equivalent to B2. And finally, A31 times x sub 1 plus A sub 32 times x sub 2 plus A sub 33 times x sub 3 is equal to B sub 3, which is the third equation. Now let us try to solve a system of linear equation using the matrix equation AX equal to 0. So say A is a 2 by 3 matrix, then we will have X is equal to x sub 1, x sub 2, x sub 3, and we have here the right side, which is equal to 0. Solution. So as a system of linear equations, we will come up with an AX equal to 0, right? So that is, we have 1 times x sub 1 minus 2 times x sub 2 plus x sub 3. This is the first equation, equivalent to 0. And then we have here 2x sub 1 plus 3x sub 2 plus negative 2 times x sub 3 equal to 0. We'll have the second linear equation. And then from there, we can continue on solving the system of equation by applying our Gauss-Jordan elimination on the augmented matrix of the system. Last time, we already learned how to perform the Gauss-Jordan elimination using elementary row operation. So this one will be the reduced row echelon form. So we see here we have a leading 1, and below that one 0, and then we have again another leading 1 here, and above that one is 0. So this one is already in reduced row echelon form, and from row 1 we can interpret the expression in row 2, okay, as, okay, are we using x sub 2? Yes, so since, therefore we can say that x sub 2 minus 4 over 7 x sub 3 is equivalent to 0, so that x sub 2 is equivalent to 4 over 7 x sub 3. Now, since there are more unknowns than the number of equations, this system of equation has infinitely many solutions, and therefore we are going to have a parametric representation of the solution. So let's say we consider x sub 3 to be the free variable, then we're going to let x sub 3 be equal to the parameter p, such that p is any real number. Then we can say that x sub 2 is equivalent to 4 over 7t, right? So if that is right, now based on this expression, we have x sub 2 is 4 over 7t. Say x sub 2 is 4 over 7t. And then with 1, okay, with 1, what do we have? So according to row 1, we read row 1 as x sub 1 minus 1 over 7 x sub 3 is 0. Okay, then we solve x sub 1 as simply 1 over 7 x sub 3 but we know x sub 3 is t, so we will have 1 over 7 times t. So we can write down the solution as simply 1 over 7t, and then we have here 4 over 7t as well as t. Now, if we want to come up with whole number, then we can allow, say, we can allow t to be equal to 7, for example, so that, right, now, if you like, you can have t as 7, so that, say, if t say if t is equivalent to 7, then you'll have the solution, say 1, 4, and 7. Okay, so depending on how you assign the value for your t, or depending on how you find the expression for your unknown variables, but definitely the solution set is in terms of a parameter. So in this case, another choice of the parameter is 70. Okay, if you allow x sub 3 to be 70 instead of t, you can also have that, so that the expression for x sub 1 is simply, so x sub 1 becomes t and x sub 2 becomes 4t, and x sub 3 equals 70 if t is any, because t is any real number. So again, whichever way you want to assign, or how you assign the parameter to your free variable, you can do that, because this system of equation has infinitely many solutions, since there are more unknowns than the equation. In matrix terminology, we found that the matrix equation, say we have the coefficient matrix multiplied by the solution vector equivalent to the constant terms, has infinitely many solutions, represented by, okay, so going back to our solution set here. Now let us make use of what is given here, that is allowing x sub 3 to be 70, so that 4 over 7 times 70, we will have your 4t for x sub 2, and for 1, you will have 3t, and for x sub 3 70. You can write it down in form. So say, for example, you will, or in column form. So we have the solution vector x consisting of x sub 1, x sub 2, x sub 3, and indicating the parameters. You have t, 40, and 70. If you factor out on t, then we will have the solution 147, where t is any scalar. As you can see here, our answer is also the same, since the particular solution is actually 147. That is multiplied by t. Now, if I regard t to be equivalent to 1, I have my solution, which consists of 1, 4, and 7, as x sub 1, x sub 2, and x sub 3 respectively. Okay, so any scalar multiple of the column matrix on the right is a solution. So here are some sample solution. You have 1 for 7. So if t is equivalent to 2, then you have 2 14. If t is equal to 0, then you have 0, 0, 0. If t is equal to negative 1, have negative 1. So all these are actually sample solutions. They are all accepted. Okay, since we remember that the solution set is E147, and we can assign any value. Now, what about partition matrices? How this apply to our system of equation? So recall that the matrix equation AX equals B can be represented in a more convenient way by partitioning the matrices A and X in the manner shown below. So again, we know that A are simply coefficients of the unknown variables x sub 1, x sub 2, up to x sub n, and you have your X which is a column vector consisting of all the unknown variables from x sub 1 up to x sub n and b, which are all the constants in the equation. So we will have a column vector consisting of b1, b2 up to b sub m. So if A are the coefficient matrix, the column matrix of unknowns, and the right-hand side respectively of the m by n linear system AX is equal to B. So these are just the partition, okay? These are just the partition matrices. So we have here your coefficient matrix multiplied to your vector that consists of all the unknowns equivalent to. Now, with your AX is equivalent to B, we can actually express the matrix product as linear combination of column vectors. Now, how do we do that? So the matrix product AX, A times X, is a linear combination of the column vectors A sub 1. So we have your first column A sub 1, second column A sub 2 up to A sub n, that form the coefficient matrix A. So what we are going to do, since, okay, you'll have your x sub 1 multiplied by column 1 plus x sub 2 times column 2 of the coefficient matrix plus up to x sub n multiplied to the last column of the coefficient matrix. So notice that if you go back to the system of equation, so you will have A11 times x sub 1 plus A12 times x sub 2 plus dot 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 A sub 1, A sub 1 n times x sub n equals B sub 1, A sub 21 times x sub 1, A sub 22 times x sub 2 plus dot 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 A sub 2 n times x sub n equal to B sub 2. Notice that the coefficients of the first column are all x sub 1. The coefficients of column 2 are all x sub 2, and the coefficients of the last column is actually x sub n. So in that regard, we simply are expressing the matrix product AX as a linear combination of all the column vectors. Hence, we will have the following. Okay, we know that again, first column of the coefficient matrix is all multiplied to x sub 1, second column of the second matrix is all multiplied to x sub 2, and so on and so forth. So that now is what you call the linear combination. So furthermore, we have with the system AX equals B is consistent if and only if B can be expressed as such linear combination where the coefficients of the linear combination are a solution of the system. So, for example, we will have here the linear system, which is made up of 3 equations and 3 unknowns. We can write it as a matrix equation AX equals B, and further write it as a linear combination of the column vectors of A. So we will have x sub 1 times column 1, is 147, plus x sub 2 times column 2, which is 258, plus x sub 3 multiplied by 369, equivalent to 0, 3, 6. So using Gaussian elimination, you can show that the system has infinitely many solutions, and one of the solution is 1 for x sub 1, 1 for x sub 2, and negative 1 for x sub 3. So if we supply it here, substitute the values of x sub 1, x sub 2, x sub 3, we can see that it will satisfy the equation. That means we have 1 plus 1 times 2, that would be 3. 3 plus negative 1 times 3 is negative 3, that is equal to 0. 1 times 4 is 4, plus 1 times 5, that would be 9. 9 plus negative 6 is 3. We have 1 times 7 plus 1 times 8, that would be 15. 15 minus 9 is 6. So, as we can see here, B can be expressed as a linear combination of the columns of B. So this representation of one column vector in terms of the others is a very important and fundamental thing of linear algebra, the concept of linear algebra. Okay, so we're done with the first topic on matrices, and for today we were able to perform operations on matrices, particularly addition, scalar multiplication, and multiplication of matrices. We were able to transform a system of linear equation into a matrix equation Ax equals B. We were able to find the solution coming from an Ax equals B form, which in turn converts it into an augmented matrix, right? So that's how we did it earlier. And we can find the solution. Also, we can express the system of equation, and we can express the matrix equation Ax equals B as a linear combination of the column vectors of A. That means if a solution is available, we can actually check whether our solution satisfies the system of equation using the linear combination form. So that would be all for today. So in the next lesson, we will be dealing now with another operation which we will call matrix inversion, which is a very important concept also in linear algebra. So see you